As mentioned in previous video, we actually talked about saying that we're going to calculate the stiffness matrix Q in terms of the unidirectional. So your matrix is, we first calculate this unidirectional composite first. Then after that, we use a certain equation to convert it as a woven roving type of material. Then we're going to use it, which is the second one. So we calculate the woven roving one. Then we use the woven roving one, if I'm not wrong, if we're going to use the woven roving one to calculate the axial stiffness. Then we calculate the ELX, our longitudinal thing, and we will go on to the next heavier part, which is finding the shear stress of your sandwich panel. So in order to do all this thing, our first step is the most important step, and therefore let's calculate the stiffness matrix Q. Alright, so if you find it not familiar or whatever, you can actually head back to this few videos. Alright, where tutorial 2 question 5, alright, where we will talk about finding the Q, finding the stiffness matrix. Alright, so in order to find the stiffness matrix, we're going to use the following formulas, and this is the one. So you're going to first find your Qij first, alright, your Q11, Q12, etc. Okay, so in order to find that, your Q11, which is E1 over 1 minus Poisson ratio 1 to and Poisson ratio to 1, things like that. So this is the equations for you to use. In case if you have forgotten, your E1 and your E2 are simply, alright, if I were to just draw all this thing, alright, this axis is the 1 axis, this is the 2 axis. So the E1 is actually the Young modulus in the 1 direction, E2 is the Young modulus of the 2 direction. Alright, hopefully it's pretty clear. And therefore the first step we're going to do is to get the somewhat the Young modulus in the 1 direction. And in order to do that, we need to have the Young modulus of the fiber and the Young modulus of the matrix, including its volume ratio. Alright, so over here in the question, we are actually given with all these informations. So I can just simply plug them in now and just check it out. Alright, my first step is actually to find E1, then to find my E2, Poisson ratio 1, 2, and Poisson ratio to 1. These are the 4 things that is standard we're gonna find every time. Okay, so my first step is to just find the E1 first. Okay, so I'll just simply plug this equation and just move it over here, which is my first step. Yeah, so is equals to the Young modulus of your fiber. So what is it? It's actually given Young modulus of your carbon fiber is this thing, 240. Okay, and multiply by a volume ratio, or your volume fraction of your fiber is actually 0.5. Okay, so therefore I'll multiply with 0.5 plus the Young modulus of the matrix or your resin is 4 GPa. Okay, and then multiply with your volume fraction of your matrix. So you know that the volume fraction of your fiber plus your volume fraction of your matrix will give you equals to 1. Since we know that this is 0.5, which is what we have shown, the volume fraction is 0.5 for fiber, so we know that the volume fraction of the matrix is 0.5 also. Okay, and therefore I'll just sub it in, and once you calculate that, we have ourselves 122 GPa. Alright, this is the Young modulus in the 1 direction. Next, I'm gonna calculate my E2. Alright, my E2 is this one, right? I use this equation. So this is the equation that you're gonna keep using. Alright, and just a mindful understanding, alright, is that for E2 is 1 divided by E2, so the volume fraction divided by Young modulus, volume fraction divided by Young modulus also, or in terms of matrix and in terms of fibers. This one is multiply, this one is divide. Alright, so in case you want to see the trends between them, so the volume fraction of a fiber is 0.5. Alright, divided by Young modulus, it's 240 GPa. So I'll just simply sub in the values only, right? So I get 0.1271. Alright, you can just do it yourself, I will not go into details. 1 over E2 is equals to this one. Take note that you're gonna find your E2, right? So you're gonna switch in between. So what you have is 1 divided by 0.1271. Yeah, is equals to your E2, where your E2 is equals to 7.86 GPa. Okay, so for the sake of making myself clear, this is my E1, this is my E2. Okay, next I will calculate my V1, my Poisson ratio 1, 2. Okay, so in standard, I find this one, you can also find this one first. It all depends on you. Alright, so for me, I find all this first. Okay, it all depends. Okay, so next is that I will just find my Poisson ratio 1 2. Okay, so your Poisson ratio 1 2, normally I'll visualize it. Or not, whenever I do V1 Poisson ratio 1 2, I'll just draw it out. You no need to draw it out, but I just want to let you know, since yeah, just to remind myself also. So this is in the one direction, this is in the two direction. So 1 2 means that it is actually a strain in the two direction, a minus strain. A minus strain, that means that it's being compressed in this direction. Alright, while you have, so this is actually sorry, my fault. Alright, so Poisson ratio 1 2 is actually telling you that you are pulling in this direction. Alright, this is expansion over compression. Alright, so therefore expansion is in the two direction while the compression is in the one direction. Alright, so V12, the meaning of Poisson ratio 1 2 is that you're pulling in this direction. Once you pull, when you pull this in this direction, the material will be somewhat compressed in this form. Alright, so therefore the compression is in the one direction. Alright, and therefore if the compression is going in the negative one, this is why we have a negative sign over here. But at any of the case, we are not using this formula. I will only use this one. Okay, I just want to show you that what is the meaning behind this Poisson ratio 1 2. So with these values, alright, so we know that this is the Poisson ratio of the fiber, which is 0.5. Poisson ratio of the matrix is 0.35, and the volume fraction and the matrix are all known already, right? So I'll just simply sub in the values only. I'll have myself 0.275 GPa. This is the Poisson ratio. Okay, and don't know why is it there's an SI unit. I don't know. It's a ratio, right? But anyway, yeah, lazy to know lah. Just let you know. Just put it like that lah. Okay. Coming to think about it, I think we don't need the GPa. Because this is in terms of a certain ratio, the Poisson ratio of the fiber, alright, is also in terms of a non SI unit. So everything over here is don't have SI unit. So it's not, there's no GPa at all. Okay, so it's just like that. Okay, and after that, after you know your V12, you can simply use this formula, alright, to find your V21. Alright, because you know your V12, your E2 and your E1 already, which is what we have calculated. Alright, this is the value of our E1, this is my value of our E2. Then recently we have calculated the Poisson ratio 1 2, and therefore we can just simply use this formula then. Alright, so I'll just put it over here. So the fourth step is to find this one. So which is equals to, my Poisson ratio is 0.275 multiplied by E2. E2 is actually 7.86. Okay, in terms of GPa. Be careful of all the SI units. Alright, divided by, alright, this is 122 GPa. Alright, your E1. Okay, so GPA, so this thing is in terms of GPA, this is in terms of GPA, so they will cancel each other. So we will have no SI unit also. So let's work out these values and see what it is. So I would have this value. Okay, and the purpose of us calculating these four things is what? If you still remember, we are going to sub it into this Q11, Q12, where they have their own values. Okay, so yeah, this is the one. So we're just simply subbing them. Alright, so I'll just take this, maybe I should just take this one will do. Okay, so the fifth step now, what we're going to do. The fifth step is pretty easy. Alright, since we know that the denominator, they all share the same denominator, so I can just work out these values first, so that I can sub in into my calculator easily. Okay, so 1 minus Poisson ratio 1 2 times 2 1 is what? So 1 minus 1 2 is this one, right? 0.275, so I'll just write. And then Poisson ratio 2 1 is 0.0177. Okay, and therefore if I were to calculate both of them, I would have 0.995. Okay, and then next is that I know that everything is in terms of 0.995 now. Okay, alright, so I can just simply sub in my E1, my these values all along, and it's pretty easy to calculate already. Alright, so in case you may find it weird, why do I calculate this thing? Alright, because I'm trying to make things easier for us. Alright, these are all the things that we have just calculated. You see, they are all the same, so I can just simply calculate the values and just plug it in. That's it. Or I no need to calculate again and again, typing all these things. It's a waste of time during exams. So therefore I'll just change, since I found the values, I'll just plug it in. Okay, so if I were to calculate for all my Q11, Q12, Q22 and Q33, my values are, for that I actually forgot the G. Alright, so I can just plug it in over here. Okay, so my G, alright, is G12. So my Poisson ratio I sub in as a Poisson ratio 1:2, and I know that my Young modulus is E2. Okay, this is the standard way of doing things. Alright, so you're gonna memorize this general formula in case that you may need it. Alright, and okay, so if I were to sub in all this value for that what we have said, and also this value, since we have all this, alright, actually this one, so my E2 is actually 7.86, or divided by 2 times 1 plus Poisson ratio 1:2. Poisson ratio 1:2 is actually 0.275, right? This is Poisson ratio 1:2, right? This one. So I'll have 0.275. Okay, so if I were to work it out, all of them, alright, my Q11, Q12, Q22 and Q33, which, yeah, so I have this value. I'll have all this value. Okay, so I'm just simply subbing in all the stuff that I've just calculated. Alright, it's all given to you. That's why I say the first 4 steps is very important. Alright, these 4 equations is standard, always come out one, always you're gonna memorize. So just take note of this 4. So once you get them, then you'll just calculate your Q values. Alright, and you have all these values. And once you sub it into the matrix, alright, this is the reduced stiffness matrix, your Q. Alright, actually you don't need to sub it in, because what we're gonna do next is to also find your Q bar UD. Okay, what I've been calculating is only QUD. QUD is unidirectional stiffness matrix. It's just a composite that has this type of phenomenon, one line like that, and it's unidirectional, only a good strength in only this direction, one direction. So it's a unidirection. Uni means it's one, so it's one direction. Okay, and therefore this is only talking about the pure stiffness matrix of the material. However, if you were to, because if you think about it, alright, just a recap also. Alright, this is your overall material. Alright, including your whatever, like your core, your faces, everything all together already. Alright, so this axis is the global axis, x and y. Okay, and while you're the one that you're calculating for a QUD, or if you think about it, is a stack on top of this. Alright, it's actually a certain 45 degrees plus minus. Alright, so in this case, if I were to draw 45 degrees, it's like that. Alright, where your axis is parallel to the fiber. This is 45 degrees. Okay, 45 degrees also. So this is 1, this is 2. Okay, so the QUD that we are calculating is only for this 2, 1 axis, right, or the local axis, and we're going to translate it to a xy, because everything is the whole shape of your material is in the xy direction. It's not slanting, right? It's not slanting. Alright, and therefore what we're going to do is to transform them. So therefore we have a Q bar. Q bar is to transform your 1, 2 direction into the xy direction, and this is why we're going to use a Q bar equation also. Alright, hopefully this is pretty clear. Okay, so this is the next step, which is the 6th step. Alright, is to get your transform stiffness matrix, your Q bar. Alright, I know it's very long, but we are almost there. So we only have a plus minus 45 degrees, right? If you were to take a look back, and this is a long time ago since we have looked at the question. Alright, so the laminate are running at an angle of plus minus 45 degrees, and that's all. There's only plus minus 45 degrees, and therefore plus minus 45 degrees is the same. Alright, so you no need to calculate 2 times. So what I mean is that if you have 2 laminates, for example, 45 degrees and 60 degrees, alright, then you're gonna sub in your angle theta, your theta over here, alright, as 45 degrees for all of them. this is only for 45 degrees. So if you have 60 degrees, you're going to have another set of this equation for 60 degrees. You're going to calculate a lot of things. So therefore, to keep it easy, alright, they give us plus minus 45 degrees. Alright, so plus minus 45 degrees, if you sub in as theta, the outcomes will always be the same. So you need to give a remarks stating that the values for q bar 1, 1, 1, 2 and all this are the same for plus minus 45 degrees because the angle doesn't affect the laminate. Alright, hopefully you get what I mean, because our face, this is our face, and then this is our core, right? And then the bottom is another face, but this face consists of two pieces of laminate. So this is two pieces. The top piece is laying in the 45 degrees, while the bottom piece, if you take a look, the bottom piece over here is laying in a minus 45 degrees. Okay, so in total they are somewhat like that. Okay, and therefore you're going to take note of that. And this is why we are calculating for two laminates. But however, because they are plus minus 45 degrees, we only calculate once only, because 45 plus 45 degrees and minus 45 degrees, we will sub it in into the theta angle, the outcome will always be the same. Okay, hopefully this is fairly clear. So I'll not go into details on subbing because it's pretty straightforward. The values in your Q11, alright, the values from your Q11, Q12, Q33, whatever, is being sub inside over here, yeah, your Q11, Q22, etc. Angle you know is 45 degrees, you can just sub in. Alright, except for the cosine 4 is cosine theta to the power of 4. So if it's 45 degrees, then you just sub in cosine 45 to the power of 4, and then you just calculate. So you just calculate for this, each of them, and then you eventually get your values for Q11 bar, etc. Okay, I'll not go into details on deriving that. So I think I will just continue to do this in a way that I'll somewhat demonstrate to you the easiness or the shortcut method in calculating all this. Alright, so the first step I'll do is to write down all this. Alright, okay, so why do I write this? Because you see, this one is in terms of cosine square, sine square, the another one is cosine 4 to the power of 4 and sine to the power of 4. There's only 4 types of trigonometry stuff. So I'll just write down the value, so you just sub it in straight away. You no need to actually type out all these things, and sometimes you type wrong and then you're going to retype again. So I'll just write down all the values so it's easier for you to check it out. But make sure that you're writing things in terms of a 45 degrees, not radian. Okay, so if you were to do that, I would have 0.5, sine will be also 0.5. If I were to find for is all these values. Okay, so it's kind of standard. If you were to do 45 degrees, for the square is 0.5, for the to the power of 4 is 0.25 if you sub in as a 45 degrees. Alright, and then over here the Q12, Q33, the values we have taken it all out, so I'll just write them now. So with these things, would it be easier if you were to calculate for this now? Alright, so because you already have all the values already, so this thing over here, instead of cosine 4 theta, you just write as 0.5, this one is 0.5, this should be 0.25, sorry. So this will be 0.25 because it's to the power of 4. The power of 4 is 0.25. Okay, so therefore this is 0.25. Alright, this thing over here is 0.5 times 0.5 because this is cosine theta square is 0.5, right? Times sine square theta is also 0.5, so yes, 0.25 also. As you can see, we have simplified the whole equation to a more simple one, and then you just multiply it because Q11 is just Q11, Q22 is just, you just sub in already. Alright, I'll not go into details on the calculations, but at least up to this stage you get to see that the efficiency of writing all this angle down. Alright, it helps you quite a fair bit when calculating things, and it's pretty easy. Alright, so I'll just simply write down the values if I were to calculate them. In fact, I didn't calculate them, but I'll just believe that the calculation will eventually give us certain values, alright, from the lecturer. So I'll have these values, okay, and I should actually write them as unidirectional because we are calculating in terms of unidirectional. Okay, and next, alright, then you can apply this equation. Okay, so to apply this equation, you can just simply use what we have done just now, right? The UD. Alright, so I have all these values already. You just sub in only. Okay, so if I were to do that, alright, my Q11 woven roving, because we need to calculate the woven roving in the Q11, which is also equals to Q22 woven roving, is half Q11 UD plus Q22 UD. So Q11 UD plus this one divided by 2. Alright, eventually you'll get this one also. Okay, and it's quite intuitive because Q11 and Q22 is the same, exactly the same, because they are 45 degrees. But anyway, so then Q12 woven roving is equals to Q12 unidirectional. So it's the 30.629. Alright, it should be 0. Alright, while Q33 is the same also, it's very straightforward. I'll have all this coming out. Alright, and this is exactly the one that is being shown from the lecturer's answers. Okay, and to some extent we have somewhat cleared away these two things. Alright, magically. So we calculate after this thing, we will use the equation, which is very simple. This is the equation that we use to just calculate, and you will get your bar coming out already. It's pretty straightforward. Okay, so we are somewhat clear away these two. Alright, and our purpose is to get this value first. Okay, we're gonna use this woven roving somewhat stiffness matrix to get our axial stiffness. Okay, but before that, I'll just also highlight to you another method to find this value. Okay, is that before that, in our section over here, alright, our so-called approach is to get our Q bar first, alright, for the Q bar unidirectional, and therefore after calculating, we calculated this thing, alright, and then we use this equation to use the UD to convert to WR. Alright, however, we can also do the other method. Alright, or instead of using the Q that we have derived, this is the Q that we have derived way earlier ago. Alright, instead of using this Q to derive our Q bar, so in other words, we use Q UD to derive Q bar UD, and then using the Q bar UD we derive Q bar woven roving. Correct? This is what we have done. Alright, now I have the alternative method where instead of doing that, you can use QUD to find QWR. Alright, and use QWR, then you find your Q bar WR. So there is another method also, which is the lecturer's method. Alright, but it's the same thing. It's just dependent on how you're going to use them. So therefore, if I were to just bring this Q11, okay, I'll just bring this over here. Okay, so as you can see, this Q11 plus Q22 UD, these are all UD lah. Okay, I'll just simply calculate them. Alright, so I'll have half. Alright, Q11 UD is actually 122.6 plus Q22 UD is what? Q22 UD is 7.899. So what I will have is 69.199, and the rest follows up. I will not go into details. So this value is for your Q11 WR woven roving. This one is for your woven roving also. These are all for your WR already. Alright, this is Q12 WR, which is corresponding to your Q12 UD. Because your Q12 WR is equals to Q12 UD. So it's exactly the same thing. I didn't change anything. Same thing for here. Because Q22 is equals Q22, I should say that this value is Q22 WR. Alright, so Q22 WR is equals to your Q11 WR, which is this value. And I think you need to work it out so you know what I mean. But this is the another method. So once you get this already, then you apply this formula again. Well, instead of these formulas for Q bar UD, alright, you will instead write it as Q bar WR. So if you were to apply it into this equation, you eventually get the same answer as our answer over here. Alright, so these are the values. Alright, so this is our Q11 bar WR equals to Q22 bar WR. Alright, this is yeah, to be more clearer. Okay, so I hope that you kind of see the different methods and techniques in applying all this formula. Alright, hopefully this is pretty clear, and therefore just a recap, a summary. Alright, in this two bigger, this calculating this Q, is that first you're gonna calculate your Q. Alright, using the old methods that we are finding the Poisson ratio, everything, the Young modulus. Once you get the values of your Q, of this Q, then which is at this point of time. Alright, at this point of time, calculating UD. Alright, you can either way go to this point, calculate your bar UD, and then calculate your bar WR, or alternatively, you can also use this thing to calculate your QWR, and using your QWR, you calculate the Q bar WR. Our objective is to calculate this thing, is to get the value of all this. And therefore, this is what we have done in the previous video. I mean, in this video, sorry, I'm being shared already. But the equations all over here, this is a very powerful equation for you to use to find your to convert your so-called WR, or sorry, to convert your UD, which is the UD to WR. So this is how you convert from unidirectional to woven-roving. Nonetheless, you can also convert back from woven-roving to unidirectional. It all depends on how you're going to use them. But this is how the methods comes about. In the next video, we'll calculate the axial stiffness and hopefully the longitudinal Young modulus, which is also pretty quite straightforward already. Because the only problem is this thing. Once you settle this, actually the later part is quite easy. And I shall see you then.